Good luck.
Thanks. So first of all, thanks to the we would like to thank the FOSDEM team to invite it for the talk and to give a bit word on Keccak. So I have a problem with the color. Okay. So that's work that we did since the 5 last year with Johan, Guido, Gilles, and myself. So Guido is not here because he's Italian. He just got a baby. So this talk will be about Keccak, so more than just SHA3SUM. So Keccak is hash functions. So what is it about? Oh, sorry. It's my mouse which is jumping around. Okay. Come on. I'm going to drop this. Sorry. Okay. So the outline first, a bit of story to explain what is it, how we come there. Then some high-level overview on Keccak. Then Johan will go more deeply into how you can use Keccak for your own purpose, or the open source community could use it. Then Gilles will go into the inside of Keccak, explaining what's really how you can implement it. And then what Keccak has an impact on the community, what the community can do for Keccak. So first, what is a hash function? So probably you already heard of hash of some sort. So probably the one on the left you know already. Huh? I guess I spoke too much of that to make the slide. I don't know. If you would like to burn things, maybe you know the one at the bottom. If you are a French speaker, you also know this hash, or that one on the top. Huh? That's axe in English. But that's not a hash function. What we are speaking about actually is this. So if you have an input message, you have a hash function, and you can then transform this input message in some digest, which is a fixed length value, like typically 128 bit. And this is widely used. And for instance, the most known today hash functions are called MD5. So probably you know MD5SUM, SHA1, SHA1SUM, and so on. So that's quite technical, so the question is, why should you care about that? And the main thing is that actually, you probably use them several times a day, even without knowing it. So if you go to the website and you authenticate, if you do digital signature, home banking, if you for instance, are using Git to do version control, and so on, you use hash functions. And recently, there have been some breaking news in crypto, and breaking usually is bad for crypto. And indeed, in 2005, and even starting before, we had bad news about MD5, which has been broken, and then broken practically, meaning that we can really produce collisions with maybe expensive computer. And we had the same with SHA1, where today we only have a theoretical break, so it's not really practically broken, but we might think that in the future it will be broken practically. And the problem is that SHA2, so the next variant of SHA1, is very similar to SHA1 and to MD5. And so NIST, which is the American standardization body, they were afraid that maybe a break will come for SHA2 as well. So in 2007, they said, okay, let's make a same competition as we had for AES, so the block cipher, and they make a call to say to the community saying, okay, please design for us a new hash function. So the question is, who answered the call? Well, we did. So that's the Keccak team. Huh? So we have Johan, Gilles, Guido, and myself. And I would like to spend a bit of time on this picture, because this picture explains why we won actually the competition. The first thing, and probably you see that, that's obvious, we are very cute. And I guess that's a very good reason that's why we've been selected. Second reason that we have here, Johan, who already won the previous NIST competition. So of course, that's a good reason to be selected. And also I think the future probably NIST won't do any competition. They will ask immediately to Johan, really easier. Then next, we have Guido here, and he's Italian. And why is it important? That's because Italians, long time before, they invented the Roman numbers. And Roman numbers, actually, in crypto, that's important because it's like homomorphic encryption. And homomorphic encryption is the process where we tell you how to do the computation, but in the end, you don't know what you have. So Roman numbers, personally, I don't understand, I cannot read them. And the last reason also is that, actually, to make this picture, we use GIMP. I guess you know GIMP? So that's the competitor of Photoshop. And the Photoshop guys, they said that GIMP is very difficult to use. So if it's so difficult, and we manage to make such a nice picture, it means that you are really smart then.
Excuse me, could you move the phone, please?
The phone is first? Okay, sorry. Yeah. Maybe this, like this is better? Okay, of course we were not the only one to answer this call, and there were many of them, actually 64. So this is a bit the picture, so there were many known names, like Ron Clivers, which is the designer of MD5. We also saw people from Bushmeyer, the designer of Skyne hash function. So there were many of them. IBM also participated, they designed Foo. So actually in the end, we were 64. And the deadline is like this. So the first competition started in 2007, the first conference in 2009. So there was actually a selection process. And after 3 conferences, the list selected then first 14 second round candidates, then finally 5 third round candidates, and then recently they selected in October 2012, they selected Keccak. Okay, so what is it really then, this Keccak thing? Keccak actually is more than just a hash function. It's what we call a sponge function. And the main difference is that you can take any message from any length and produce another message of any length. And there are some technical properties that we will just not mention here. But mainly the main thing is that it's much more flexible than hash functions. And you have 2 parameters. So you can see here, actually in the process, you see that we have initial state, and then you have some bit going through, and you can select the width of this data path. And there are 2 names for the rate, which basically define the speed of the function, and then the capacity, which defines the level of security you can achieve with the construction. And the F, that's actually a permutation that we call Keccak F. So what is it? Actually, we have, in Keccak, we have 7 permutations. And these permutations, they have different widths. So we start from a small toy variant, which is only 25-bit wide, up to 1,600 bit wide. So basically, the small one is more for toy to play with, to analyze it, where the biggest one is really to get the most speed from the sponge function. And you can use middle one, for instance, for lightweight applications, for instance, for embedded systems and so on. So basically, these permutations, they are applied to some 3-dimensional state that you can see more or less on the left. And the thing is that you have more or less 25 what we call lanes, and each of these lanes is 64-bit wide for the biggest variant. For the smallest variants, you only have 1-bit lane, then 2-bit lane, 4-bit lane, and so on. So typically, if you have a 64-bit computer, you would use the 64-bit word of the computer to map on a lane. So basically, that's a bit like a block cipher, but you don't have a key. And how you use that? First, you have to choose one of the 7 permutations. For instance, you pick the biggest one, the 1,600, and then you have to choose the value of the rate and the capacity. Of course, the requirement is that the rate plus the capacity needs to be equal to 1,600, so the width of the permutation. And depending on your choice, here you see you have a different trade-off of speed and security. For instance, if you have chosen a capacity of 256, that gives you more or less a security of what we call 128, so you would require, in some condition, up to 2 to the 128 operations to break the hash function. And this is the speed that you get compared to what we call the reference, which is this one. But you can, if you are not happy with that level of security, you can choose a biggest rate, for instance this one, and then you get a better security, but you lose a bit of the speed. And this is different from SHA2, for instance, because SHA2, they always give you a fixed width, and you cannot change. You cannot tune it really easily to your application. So here, the trade-off, you can make it very easily. So if you are, for instance, you have less requirements in security, you can reduce the capacity and have a bit of more speed. So now Johan is going to tell you how you can use this beast for your application.
Yeah. Can you hear me? Okay, so it was so Keccak was in the SHA3 contest as a hash function, but it's in fact more than hashing, as Mika already said. It's a sponge function, and in fact, with this function you can do all symmetric crypto operations that you need. So it's hashing, but also key derivation, message authentication, encryption, the combination of message authentication and encryption in one primitive also. So I will show that on the next slides. And all these things can also be done, of course, by a block cipher. But in a block cipher, it becomes reasonably complex to define all these modes. For instance, authenticated encryption modes are not trivial to specify, while for this Keccak, for the permutation, it's more simple and straightforward. And it allows you to also, gives you more flexibility because you can choose the rate and the capacity. It's also easy to understand the security claim. So in general, in cryptography, it is, you cannot prove that something is secure. What you can do is you can claim that something is secure and then wait for people to attack. And if there are no attacks, and it takes years, then people can gain confidence in the cryptography. But for that, you need to specify a clear security claim. So you can say, okay, you will do everything with one primitive. That's a kind of monoculture. Huh? So that's reasonably dangerous, because if this single thing is then broken, then everything is broken. But in fact, it's quite the opposite if you look at the big picture. If you look at, for instance, the existing standards, SHA-1 and SHA-2, they are built using completely different building blocks than Keccak. They are based on things like addition and the combination of addition and XORs, while Keccak does not use addition. Another set of standards is based on the block cipher AES, and that's still another thing. So if you look at this big picture of standards, this will enrich the existing standards and introduce, in fact, a new basis for security. Okay, so the first application, of course, is hashing, because it was a submission to the hash contest. And what you there do is you just truncate the output to some length. So if you want a 160-bit hash, like SHA-1, you just truncate to 160 bits. If you want something of length 256 bits, yeah, you just truncate to 256 bits. So Mikael already gave some examples of where hash functions are used. So here are some more examples. So for instance, in electronic signatures, they are used. So if you do an electronic signature, you do a public key operation like RSA or elliptic curve on a message. But if you would have to do that on a very long message, like say a document of 1 megabyte, that would take a long time. So for that reason, this message is compressed to a hash, and it's in fact the hash that is signed. So some standards, there are X509, that's a standard for certificates. There is the GPG, so what's it, GNU privacy, yeah, or PGP, yeah, the more commercial version. And in these applications, it's important that it's difficult to generate two different inputs with the same output, so with the same digest. So we call that property of a hash function collision resistance. Then also for data integrity, yeah, so SHA3SUM, as Mikael already said, so SHA3SUM or SHA2SUM or whatever, MD5SUM. And then in many systems, hash functions are used to generate identifiers, like in version control systems like Git or Mercurial. Also online antivirus programs use it. Peer-to-peer systems all use hashes as identifiers. So also there it's important that each identifier is unique per input. Now, of course, because the output is shorter than the input, there will be collisions, but it's very hard to generate collisions. So that's the point of a hash function. It's hard to generate collisions. Another application of hash functions is the storage of passwords. So if you have your system where you log on, you type in a password, so the password must be somewhere present on the system to verify whether your password that you typed in is correct. And they don't store the password in the clear, they store it in fact as a hashed version of the password. In this application, it's important that a hash function is one way, or we call it pre-image resistant. That's more the official term, but you can see it as one way. So it should be hard to, given the output, compute the input. So if you have a hash of a password, it should be hard to generate the input. So even if you get hold of this file with the password, the hashed password, it should be hard to get the password from it. But of course, what you can do, if you have a file with hashed passwords, you can just try different passwords and see if the hash matches. You can always do this attack. So if you have a file with one password, then you have to try passwords until you get the right one. If you have a file of 1 million passwords, then you just try, and it's very likely that you will have some good hits. If you try the word password, for instance, it could be that in 1 million people, there will always be some people stupid enough to choose the password. So for that reason, they add salt to the input. So they don't store the hash of the password alone, they also store a salt, which is a random value. And in that way, that makes such attacks more difficult, because the salt will be different from one password to the other. There are other methods to attack this, so-called rainbow tables, and the salt also helps against that. Okay, so another method is to protect against these exhaustive password searches is to make the hash function very slow. And you can make, I didn't even explain how you add the salt. So in fact, a salted hash function, to build it with Keccak is very easy. You just prepend the salt to the message. So another method is to make the function very slow. In that case, you just append to the message a long series of zeros. This makes the function very slow, which is, in fact, a bad thing for the attacker, because he has to do a lot of these hash function computations. For a normal user, well, if he logs in, the login will take maybe 100 milliseconds more time. So it will just be a little bit slower, but it's in many systems slow anyway, so we will not notice it. So a hash function generates, from a long message, a short imprint. But in many applications, this is not enough. So if you have, for instance, SHA1, you generate 160 bits, but in many systems you need more than that. So what is typically done in all these systems is that you compute a hash and then you expand the hash again with a dedicated construction called mask generating function. With Keccak, or sponge functions in general, you don't have to expand it, you just apply the function as it is and it comes all by itself. So this is, for instance, used in SSL and TLS for key derivation. So in the beginning of, when you do an SSL session, in the beginning there is a key setup, and during the key setup there is a session keys generated, and in that generation of the session keys, you use a key derivation function, so this mask generating function. It's also used in public key cryptography for electronic signatures, encryption, or key establishment, which is defined in a lot of standards, and it's applied all the time. So for instance, in your SSL sessions, you also have an exchange of certificates, and in these certificates, these are based on these kind of standards. Okay, so if you want to send a message to another party, and you want to authenticate the message so that the other party knows that the message comes from you and has not been modified in between, you can generate a MAC, a message authentication code. And the message authentication code is like a kind of signature computed over a message and a key. So if you want to use Keccak for that purpose, you just have to concatenate the key and the pilot message in the input, and what comes out is the MAC. There are systems, most MACs nowadays are computed with block ciphers or hash functions. For block ciphers, you really have to take care in defining this MAC mode, otherwise it's not secure. For hash functions, there is an established way to do it. It's called HMAC. It's a NIST standard. And basically, you have to do some complicated stuff at the end. That Keccak is no longer needed. So why do you have to do this complicated stuff at the end? Well, there is in fact a weakness in SHA1 and SHA2, which is well known, which has been well known for, I think, 15 years. And this HMAC is there to plug this security hole in SHA-1 and SHA-2. So in Keccak, this security hole has been removed. In fact, in all SHA-3 finalists, this security hole was removed. So this makes MAC generation more simple. So you can generate a long output, as I said. So you can also use Keccak for stream encryption. So basically what you do is you feed, instead of a key, you feed a key and a nonce, a value that should be unique. And out comes a long stream of bits, and you can add this stream of bits bitwise to your message, and that does the encryption. So I've shown you on the previous slide how to compute a MAC, how to do encryption, and in many cases people want both. They want encryption and MAC, so they want to protect the confidentiality of a message, but also the integrity of the message. You can, of course, do these two things independently, but then the cost is double. It doubles the cost. Huh? So you have to do, in fact, 2 computations of Keccak of this thing. So, in fact, we took a close look and we found out that you can do this and still be secure. So you can, at the same time, generate a key stream and generate a MAC with just 1 execution of Keccak. These are things that are used in also SSL and TLS, SSH, IPsec. So in many cases, in many protocols, this is what you need, encryption and authentication at the same time. Now this is not a straightforward application of the sponge construction. In fact, according to the sponge construction, you cannot do this because we absorb data, so the padded message is absorbed and the key stream is squeezed at the same time. And normally there's first an absorb phase and then a squeeze phase. But we defined a kind of a sister construction to the sponge called duplex, which can be shown from security point of view equivalent to the sponge. You can also use this, for instance, for random generator, a deterministic random generator that allows reseeding, so that allows to input new randomness while it is running. Okay, so now the security claim. What is the security? Michael already said that the security of Keccak or a sponge function in general is defined by its capacity. So we have made an application, well, a colleague of us has made an application that is available on our site, so you get the URL there, where you can, in fact, give your security requirements with respect to 2 criteria and see what then the requirement is on the capacity. So we first have the required collision resistance. So the problem to generate 2 inputs that give the same output is expressed as 2 to the power x, where this 2 to the power x stands for 2 to the power x calls to Keccak. If you want there a security level 2 to the power x, then you fill in there this value x in the top case. There's a second criterion which we allow you to fill in is the pre-image resistance. So the effort to generate, given an output, to generate a matching input. So for instance, if you have the hash of a password to find a password. So you can fill something in. So for instance, here we fill in 128. So what is so special about 128? 128, that's nowadays considered to be the standard security level of encryption. So the AES, the shortest block length, the shortest key length of AES is 128 bit. So let's say we want a collision resistance of 2 to the power 128 and also the pre-image resistance of 2 to the power 128. Then this allows you to choose a parameter, the parameters that are shown below, so you get a capacity of 256 bits is sufficient. So you see it's the double of 128. So for speed, this gives you on Intel Core Duo 9.6 cycles per byte. So if you fill in another required resistance. So if you say, okay, we want for pre-image resistance, we want 256 bit of security. So we want to find a pre-image to cost about 2 to the power 256 calls to Keccak. Then, in fact, the capacity becomes 512. So with the capacity growing, the rate becomes less, and the amount, so the rate is the number of bits that you can process per call to the Keccak F permutation. So the speed goes down. So now a message, hashing a message, or applying Keccak to a message costs 12 cycles per byte. So it's slightly less fast. Okay, so in fact, we have defined a security claim called a flat sponge claim for a given capacity. So if the capacity is, for instance, 256, then we claim that the Keccak resists any attack up to 2 to the power 128 operations. So in fact, for a given capacity, it's 2 to the power c divided by 2 operations. Below that complexity, an attack should be, have a negligible success probability. Unless you can also do it in general, so for any function. Let's say you would have Keccak truncated to 1 byte. Well, finding a pre-image of 1 byte, you just try enough values until you hit the right byte. Eh? And there are only 256 different bytes, so you cannot have a better security level than 1 over 256. So 2 to the power 128, what does that represent? So we put something on the slide to give you an idea. If you have 1 billion computers, and these computers can each perform 1 billion evaluations of Keccak F, so that's the permutation in Keccak, it would take you 10 to the power 13 years to evaluate this permutation, 2 to the power 120, 2 to the power 128 times. So that's about 700 times the age of the universe. It was, until recently, a claimed security level of 2 to the power 256 was considered quite normal. Well, let's see what it gives when you have that kind of claim. Then, in fact, this 1 billion computers, that will take, well, a factor 2 to 10 to the power 41 times the estimated age of the universe. But you can say, okay, we can build more efficient computers, so let's assume we can build the ideal computer, an irreversible computer. It takes a minimum amount of energy to compute 1 bit. Then, in fact, to compute from 1 to 2 to the power 256 would take the total energy output of the sun during 10 to the power 20 years. So, yeah, it's a bit ridiculous security claim. So now Gilles will continue about the inner workings of Keccak.
Okay, so so far we spoke a lot about sponge functions, how to use it. And if you take a look at the pictures of sponge functions, there is this F function, the permutation, and the bulk of the work of Keccak is really done inside this F function. So I'm going to say dive into Keccak F. So if you take a look at our website, we have this description of Keccak F in pseudocode. So Keccak F is just the repetition of 24 rounds for the case of the largest permutation. So 24 times the same kind of operation is performed. That's the top part here. And, oops, I didn't click on anything. So 24 times the same kind of operation, except that there is a round constant, so something that changes from round to round. On the bottom part of the pseudocode, you have the description of what's inside the round function. And we like to put Greek names on the operations we do. So first, the theta step. It's really a linear mapping. I should first say that, okay, the A, B, C, and D's are arrays of, say, for instance, 64-bit values. So Michael was speaking about a 3D state. So here we have 2 coordinates, x and y, and the z coordinate is the set of bits inside one word. So A of x, y is, for instance, 64 bits, and the z coordinate is the location of the bits inside the word. So in the theta step, you have a bunch of XORs, 1 rotation by 1 bit over 64 bits, and that's it. In the rho and p steps, it's just, we just move things around and add some rotations to change the bits within each of these lanes of each of these 64-bit words. Then the key step, so that's the nonlinear part of Keccak F. So in any good symmetric cryptographic function, you need some nonlinearity. So that's the purpose of the key step. So you have a bunch of XORs, not and ANDs. And then finally, one of these words, we just XOR the round constant. So it's quite easy to describe, I think. and the operations that are involved are just XORs and not and rotations. So what does it give in terms of software speed? Okay, for the finalists, the 5 SHA3 finalists, Keccak was not the fastest in software. Yet on the modern PCs, we can see that actually Keccak is faster than SHA2. We show this example, which is honestly quite favorable to Keccak, but it's on AMD Bulldozer. But if you take a look at the numbers, for instance, on Intel Sandy Bridge, you can get similar numbers. So what you can see is that Keccak is faster than SHA2 on these kind of machines. But also, if you allow Keccak to be used in a mode where you can exploit parallelism by computing 2 Keccaks at the same time using a 3-hashing mode, then you can actually be even faster, and in this case, be faster than MD5. Okay, so on another CPU, for instance, the Sandy Bridge, MD5 is going to be slightly faster than the Keccak tree, but MD5 is broken, and so far, as far as we know, Keccak is not yet broken. So still, it's pretty fast, I think. During the competition, Keccak was really impressive in terms of speed for hardware implementations. So it's really, really much faster than any of the other finalists and much faster than SHA2. So for the future, it's interesting because nowadays we have this AES instruction in CPUs. Maybe later, hardware vendors will integrate some kind of coprocessor for SHA3, hopefully, or an instruction in the CPUs. We'll see what goes on, but the speed in hardware is really an advantage for Keccak. Okay, so I was mentioning in this pseudocode that we have 64-bit rotations. Now assume that you have a 32-bit CPU and you want to implement Keccak. Then you're going to have to put a lane, so 64 bits, on 2 32-bit words. And then the 64-bit rotations, they will be hard to implement because one word by rotation will spill the bits to the next word, and the next word will spill bit to the first word. So that's kind of tricky and inefficient. Now, there's a trick that is actually quite specific to Keccak, is that instead of coding the first 32 bits in one word and the last 32 bits in the other word, you just put all the bits that are at even positions in one word and all the bits that are in odd positions in the next word. Then the 64-bit rotation really becomes 2 rotations over 32 bits each. So we can really re-express everything in Keccak in terms of 32-bit operations. Instead of applying 64-bit operations on 25 64-bit words, we can do something else on 50 32-bit words, including the rotations. So that makes the implementation of Keccak also efficient on 32-bit platforms, something that is quite unique to Keccak, because as soon as you have a modular addition, you cannot use this trick, because you have the carries that you have to take care about, and that's not possible anymore. Of course, it can be generalized to other word sizes and so on. And why is it also interesting? If you take SHA-256 and SHA-512 and you compare them, you can realize that actually it's almost the same function, except that one is applied on 32-bit words and the other one on 64-bit words. So if you have to choose a security level, and you have to choose between SHA-256 and SHA-512, you're also choosing the platform on which it will run best. And you might turn into a kind of mismatch situation where you want SHA-512, but you have a 32-bit platform, or vice versa. And in Keccak, you don't have this effect. You choose the security level independently of the, okay, thank you, of the target platform. So I'm going to hurry up. And so, okay, so what Keccak can bring to the community, and what can the community bring to Keccak? So first, let me give you some words about the SHA3 contest in itself. So the SHA3 contest in itself was really something open. It was required by NIST that every submission should be public. All the details of the algorithm should be public, And this allowed the cryptanalysis. Everyone could try to break and find flaws on the competitors, for instance. So that was really open from that perspective, from crypto research perspective. Also, all the optimized and reference implementations had to be open source. So this allowed open benchmarks. So, for instance, eBash and XBX are really nice examples of benchmarks of all the candidates. And for Keccak, we try to do something a little extra, which is Keccak tools. So for our purposes, we also wanted to of course, to look at the security of Keccak. And doing cryptanalysis, we needed tools to analyze the properties in terms of linear and differential cryptanalysis. And at some point, we decided to publish the routines that we used for the analysis, and this created Keccak tools, which is, of course, open source. So the idea is to encourage cryptanalysis, not only for us, but of course, but also for the others, and also to allow people to verify our claims. If we say that, okay, Keccak has this property in terms of differential cryptanalysis, but we also publish the associated code that helps verify these claims. And as a byproduct, Keccak tools can also generate some optimized code for Keccak. I will mention this again later. Then at some point during the computation, there was not so many attacks on Keccak. So for us, it was good news. It meant, okay, Keccak is not so easy to break, hopefully. But on the other hand, some people would say, okay, maybe not so many people looked at it, it's too new, so maybe it's not a safe choice. So we really wanted to encourage cryptanalysis, and at some point we decided to give some little awards, not something so big in terms of money, to the best cryptanalysis results every 6 months or so. And so we gave some Belgian Trappist beer, including West Vleteren, to Jean-Philippe Aumasson and Dmitry Kovatovich. Guido bought a very nice Italian coffee machine. I gave also to Jean-Philippe and Willy Meyer. Then again some beers to two French girls, and then some chocolates to Dan Lunstein. Nowadays we changed our mind in terms of how to encourage cryptanalysis of Keccak. Instead we set up fixed we publish challenges that have to be broken on some weakened versions of Keccak, so versions of Keccak with less rounds. So far, we have pre-images for 1 and 2 rounds on some instances, and collision on 1 to 4 rounds. And this contest is still open. So if you wish, you can take a look and try to break some of these challenges. So you won't get rich either with this contest, but I think it's nice. It sets really concrete targets for cryptanalysis. Moving towards implementations, we also wanted to encourage implementations of Keccak on some exotic platforms, and it turned out that the two best, most original implementations were 2 implementations on a GPU, on a graphics processor, 2 different instances of Keccak. Okay, so let's talk about implementations. If you go on our website, you will find 2 kinds of implementations. One set of implementations are reference implementations. There, the goal is to have readable code, something that can be checked and you are sure it's correct. You have some in C, in C++, in Python. And then another set of implementations are all the optimized implementations. And we wrote some, and some of our, one of our colleagues, Ronnie, wrote some code for 8-bit, 32-bit CPUs that includes the bit interleaving technique I mentioned earlier, 64-bit platforms, and even using SSC and variants. Some of these implementations are in C, some in assembly, especially ARM and AVR. For x86, I don't think we managed to beat GCC actually, but you can try. Please do so. Some of the implementations are in place, so that's to reduce the RAM usage. And I mentioned it, so we have some optimization techniques that are implemented in Keccak tools to help you generate code that really fits for Keccak. So all these implementations are available, but I guess we are more cryptographers than developers, and the consequence of that is that we don't have a consistent library that you could compile on your machine and that will select the best optimized implementation for the machine it's been compiled on. So if you want, if you have time, you can help and try to take these implementations and try to make a consistent library, dynamic or static library. You can also try to optimize these implementations. Probably you can do better than we did, or you can even write your own application in your own implementation in your favorite language. We have this document, the Keccak implementation overview, that gives some implementation and optimization techniques that you might want to read before diving into such a work. We just wish to say two things about the interface. So first, the SHA3 standard is not out yet. Of course, Keccak has been selected as SHA3, but we don't know exactly what NIST is going to do. So we don't expect them to change Keccak in any way, but there might be little details here and there that will make SHA3 different from Keccak. At least SHA3 might be a subset of Keccak, like AS is a subset of Rheindal. And I think that the best way to be future-proof is try to stick to the definition of sponge and duplex, to have a consistent API, consistent with the definition we put on sponge and duplex, because I don't think that NIST will try to change that level of abstraction. So yeah, if you have time, please go ahead. And that's about it I had to say. Some credits for the pictures we used in the presentation, and if you have any questions, please raise your hands. Thank you.
Hello, thank you for your great work on this talk. I would like to ask you, you were referring, some of you, I don't know which one of you was, to make the key derivation slow, right? There's a new trend. People also want to make it big, right, in memory. How does Keccak fare in memory? Can you make it really, really memory hard?
I didn't get the question.
You mean that these implementations should take a lot of memory?
Yes,
Yeah,
that's the point.
Yeah, Keccak by itself doesn't use a lot of memory, but you could define a mode on top of Keccak that would use a lot of memory. So you mean like things like script, I guess? Huh?
I'm referring to script and these other.
Yes, yes. So no, Keccak is not. Then you have to define a mode on top. So what I showed there on the slide was just to make it slow, but not to make it big. Yeah.
Thank you again for the wonderful talk. My question is, so a lot of us are developers, we don't often jump to crypto primitives like libraries when we're coding our applications. We tend to stick to, existing libraries that use the primitives for us. I'm thinking of like OpenSSL and other libraries where we're not actually, we're not crotch deep up in the crypto primitives. So my question is, oh, there we go. I'm sorry. My question is, how is sort of like Keccak progressing when it comes to adoption by existing libraries, like DJB's library, OpenSSL library? Are you guys doing any sort of pushing into the community to get that integrated into stuff that us developers actually use?
We're not pushing, we're not putting energy in trying to push, but of course we hope that the adoption of Keccak as SHA3 standard will help people to, of course, to jump in and try to integrate Keccak in OpenSSL, for instance. Maybe some people fear that because it's not, the SHA3 is not fixed yet, they also might want to wait. We don't know exactly.
For example, Python recently.
On this respect, our message is that we don't expect this to change Keccak in any way. Just maybe reduce the set of parameters that are allowed, or something like that.
But anyway, for example, Python has already recently implemented the Keccak version. Yeah, that's just an example.
Hello. Future in the press, it is stated that in the future there will be quantum computers, and quantum computers will break the crypto as we know it. How will this brand new primitive withstand such claims?
Okay, thank you for asking the question. Actually, quantum computers are good at factoring numbers, and that's really applicable, for instance, to the RSA scheme. For the symmetric crypto, there are some quantum algorithms that can speed up, for instance, the search of preimages. But basically what it does is a square root kind of thing, and actually we would be back to the usual security claim to the C divided by 2. So for quantum computers on Keccak, with the current security claim we have, it wouldn't change the security claim. So no problem. Hopefully no problem.
Any other question? Okay.
Hello. My question is about the duration and the maturation of the algorithm. You show on one of the first slides that the algorithm was proposed in 2007, and since the last 5 years, don't you find improvements in it?
Okay, so the question was, we submitted the algorithm in 2008 actually, and did we find improvements to make? Okay, we didn't want to change anything in the algorithm because it would invalidate the cryptanalysis done so far. So we tried to not change anything. What we did change is increase the number of rounds to increase the safety margin because of some attacks or pseudo attacks were given, but that's about it. We didn't change anything for the purpose of not invalidating the cryptanalysis.
Okay, I am very sorry, but the time is running out. So if you probably can interrupt Day just after this talk, and we have something like 2 minutes before the next talk. So thank you very much.